Let's talk about solving ordinary differential equations with Runge-Kutta methods. I want to go into deeper material, but this is a good place to start so we have a good way of understanding the basis behind the numerical methods. So the most basic numerical method for solving an ODE, where we write an ODE as u prime equals f of t u, is the Euler method. And the way we get the Euler method is just that delta u over delta t, this is another way of writing u prime, this equals f of t sub n u sub n, where we're at a specific point or a time point t sub n. And when we move this over, then we say that delta u equals f of t sub n u sub n times delta t, but this is now the future time point minus the previous time point. And when we move that u sub n over, we have that u sub n plus 1 equals u sub n plus delta t times f of t sub n u sub n. And this method right here is Euler's method. So the first way we might want to improve Euler's method is to understand a little bit about its general form. Right? So what we're basically saying is that u sub n plus 1 equals u sub n plus delta t times a derivative estimate. And now we can say, well, the derivative estimate that we used was the one at the left. So if we're to draw this, we have our current function up to here. At time t sub n, we have u sub n, and we want to get the value at t sub n plus 1, what the Euler method is doing is it takes the current derivative and extrapolates it out linearly, and that's the point that we call u sub n plus 1. So the Euler method uses the point on the left of the interval to extrapolate across the whole interval. But what if we had a better idea for what the derivative was? Right, so can you take a guess on what a good derivative to use is? Correct, yes. I heard you there. You said that the middle, right? So t sub n plus 1/2. If we knew the point in the middle, then we'd say, well, the derivative in the middle is probably the best derivative estimate for the whole interval. So, well, we'd need to know what the value in the middle was in order to do that. The way that we can do that is to just use Euler's method to get a value in the middle, then use that derivative. So we can say that u sub n plus 1/2, this value is just u sub n plus delta t over 2 f of t sub n u sub n. Right, this is Euler's method to get to 1/2 of the way. And now we can do the rest of the way via the Euler's method changed, where now what we're going to use as our derivative is the derivative at this midpoint value. This right here is called the explicit midpoint method. But let's take a look at the structure that we have here. So the way that we'd write this down is that we have a function call. So we have a k1 equals delta t f of t sub n u sub n. And from there we get a g1, which is equal to u sub n plus 1/2 of k1. Right, so this is, since this is k1 right here, u sub n plus 1/2 of k1 is our first value. And now the next function call is k2, which is delta t times f of t sub n plus 1/2. And this value right here, which is g sub 1. And now our u sub n plus 1 is equal to u sub n plus delta t times, well, this delta t f right here, this is just k2. So notice that these k's are some kind of derivative estimate scaled with t, And these g's are value estimates. And so what we can say is that we can have a function call to give us a derivative approximation. Then we use that to get a value. We use the new value to get a new derivative, and then we use the new derivative to get a new value. And we can keep on chaining this arbitrarily. So we can say that k1 is always going to be this delta t f of t sub n. Well, let's say for now it's going to be explicit t sub n u sub n. g1 is equal to some u sub n plus a1 1 k1. Right, so we can put any number here to add this, and we can say k2 is equal to delta t f of t sub n plus c sub I. Right, so we can go forward by any, or c sub c2. So we can go forward by any amount. We chose 1/2, but we could actually have chosen any value. And what we can put in here is this g1, and we can keep on chaining this. So that way we have k sub n equals delta t times f of t sub, oh, I don't want to use n, let's use m. So t sub n plus cm. And then we can use a gm, where this gm was defined as some u sub n plus a m1 k1 plus a m2 k2. Right, so all of the previous k's to a m minus 1 km minus 1. Right, so we can keep on chaining together derivative estimate, value estimate, derivative estimate, value estimate. And this general form where you can say there's any value that you can do it at, there's any way that you can linear combine them, and at the very end, your newest value, your step forward, is going to be a previous value plus some linear combination of the k's, where we call this s, the number of stages. The next value is just going to be the previous value plus some linear combination of the k's. And these three formulas right here define a Runge-Kutta method. So Runge-Kutta, Runge-Kutta method. So Runge-Kutta method is actually a very general form. You normally can write this down as some tableau, where you can say that this is a, well, you leave a space, so the diagonal is actually empty, and then you have a21, a2, a31, a32, a41, a42, ... and you have this whole lower triangle, and then you have your c2, c3, ... and c1 is always equal to 0, at least in our examples above. You have b1, b2, b3, ... and these are all numbers, and when you pick these numbers you get a method, where this method is defined as, you would simply calculate a derivative using the point, you add them together using what's in this matrix, you calculate a derivative, you add it together, you calculate a derivative, you add it together, and these are a Runge-Kutta method. So a table of values, known as a butcher table, defines what a Runge-Kutta method would be. Now, I did show you here that this was, a lower triangular matrix. When it's lower triangular, you get a explicit Runge-Kutta method. When you have this be a full matrix, then your value for k can have g's, which depend on values of k in the future. So you get an implicit equation in what your f is, and that is called an implicit Runge-Kutta method. But either way, it actually follows the same formula or the same style, and so it doesn't really matter which one you choose. So I want to just point out a very famous Runge-Kutta method. If you type in, let's see here, I can't get to. So the Dormand-Prince method. So the Dormand-Prince method is defined by one of these butcher tableaus. So the last thing here is you see that there's a second row inside of the B matrix at the bottom. So what you can actually do here is you can have these B1 tilde, B2 tilde, ... such that you have u sub n plus 1 be come from the first row, and u sub n plus 1 tilde come from the second row. This means that with every step, you very cheaply can calculate two results for what the future will be, right? So you can have this second one be, let's say, fourth order, while your true update step is fifth order. By having them be one order different, then you know that one of them is going to have a higher error than the other, and this is where adaptive methods come from. So that'll be the topic of one of these other videos, but I just wanted to go through what a full Runge-Kutta method looks like. A full Runge-Kutta method is just a chaining of calculating f derivatives at different points, computing new values at that point, computing another derivative, and then adding them together with a linear combination. And the choice of the coefficients for these combinations is the Runge-Kutta method that you choose. So the Runge-Kutta method is just one of very many Runge-Kutta methods, and if you think about it, the Euler method is the Runge-Kutta method with only one row up here, and the explicit midpoint method is now just a two-row Runge-Kutta method. But all of these methods are then just in this general form, so you can ask the question, for what coefficients do I decrease the amount of work and also decrease the error the fastest? And this is where Runge-Kutta theory comes in. We're not going to go over Runge-Kutta theory, but just know that the crazy Dormand-Prince method that I showed is one of these methods that you get when you try to optimize your coefficient choices.